Okay, let's have a look at these now. I was just planning on doing the non-theory question, theory questions first, and then the practical questions then in the next video, and then there's the tech. There's quite a few. Yeah, I think it'll take a while to get through this. Let's get started anyways. Let's get stuck in. When you find a maximum for an optimization problem, why do you need to check the signs of the derivative around the critical points? To check if it is a max or a min. Also, to confirm it's not a saddle point. Okay. Why do you need to check the endpoints for optimization? Because there could be global max min there. True or false, for every continuous nonlinear function you can find an x that maximizes min. I guess kind of false, I suppose, because if you have the function like fx equals ex, then the x is not a real number that maximizes it. True or false, for every continuous non-constant function on a closed finite domain, there exists at least one x that minimizes or maximizes it. That's true. That's true, but how can we prove it? For every continuous, good, non-constant function on a closed finite domain. How can we show that? How can we prove that? I'm thinking of the mean value theorem, but I don't think the mean value theorem helps, because the mean value theorem says there exists a C in AB such that f derivative of C equals FB minus FA over B minus A, but that's not zero. There is another theorem I think that could be useful, but I need to check the notes to see which theorems they covered. Which ones can we use? And of course, they do this quite a lot in this book. The kind of trickier ones, the nitty grittier ones, tend to be even questions, I've noticed sometimes. Yeah, no, I don't think it was an accident that it was this way around. So, every continuous non-constant function on a closed finite domain, there exists at least one x that minimizes or maximizes the function. How could I prove that now? What theorem could I use to prove that? So I don't think it's false, because I can't think of an example where that wouldn't work. um, 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 mm. Could it be false? I'm just thinking, could I make it false? Oh man, I'm gonna try something. I'm gonna try something. Consider f um, continuous, not constant on AB. And we'll define g of x equals, let me think about how I want to do this. I want to make it um, f of x minus f of a times 1 plus x minus a. Just out of space already. G of x equals f of x minus f of a times 1 minus x plus a. So that means when x is a, we'll get 0. And then plus f of x minus f of b, 1 minus x plus b. So when, no, that's not going to quite work. When x is a, this will go. And that will be 1, how about if I just put this over 1 minus a plus b, so they'll cancel, and I'll be left with fa minus fb. And then here, when x is b, no, that's not going to work. No, okay, let me pause the video and think about this a little bit more. Okay, I was trying to map it so that A corresponds with A and B with B, but I decided it'd be a little bit easier if I just go with it like this. So what I've made is a function g, and g is continuous on no, I shouldn't. I can't say 0, 1 because I don't know if f is. Oh yeah, I do have to match it up with a and b. Okay. All right. So I should change x then. not x. So 0, so I need 0, 1 to map to AB. So instead of B, so when it's, no, actually this would work actually, because there's no X inside of the, yeah, there's no X inside of the F. I kind of do want there the X to be inside of it. Okay. I'm gonna have to think about this more. Okay, let me pause again. Okay, so I've figured out the function. I'm going to call this function g equal to this. And the reason for that is g is continuous on AB, since f is. And also, g of A equals g of B, which equals 0. So that means there exists a C such that g derivative of C equals 0. G of B minus G of A over B minus A equals 0. Okay. So that means the derivative here, the derivative of this is 0 as well. So we'll need to use the product rule. So, well, it's not really the product rule. It is the product rule, actually. Yeah, so that's gone because it's a constant. So B minus A. So f times x. So that would be f derivative x times x plus fx. Well, actually C, really. Minus A f derivative C equals 0. So that's gone. So can I get this to say that f derivative has to be 0? Maybe this isn't going to work. That means f derivative C times C minus A equals minus FC. I can show there's a point where the derivative is proportional to the height. Oh, okay. This didn't work. I have to think more about this. So I had to look this up, to be honest, and unfortunately, the proof it's called the extreme value theorem, but it requires a theorem that's not in the book. So I'm not sure how they expect the student to prove this. Maybe you're supposed to do some independent research. So anyways, because f is continuous, not constant a, b, that means by the boundedness theorem that it's bounded. So that means then there exists an m as a least upper bound. Now, if there exists a c such that f of c equals this m, then that means we're done. It's reached the maximum. So otherwise, assume that f of c is less than m. Now, define, or I guess we could just say f of x is less than m, that there is no c. X is in AB. I should have said there exists a c in AB. So define a new function g of x, which is equal to 1 over f of x minus m. This is also continuous and therefore bounded. So that means there exists a k whereby g of x is less than this k. So that means, I think if I'm doing this correctly, 1 over f of x minus m is less than k, which means, and this will be, fx is always, oh, do I want to say m minus fx? Maybe I do. Yeah, actually I realize I do, because I want to keep it positive. So I'll put it the other way around, m minus fx. So that stays positive then. And that makes my life easier, because then when I cross multiply, I just have 1 is less than km minus kfx, which means fx is less than m minus 1 over k. And it kind of contradicts what we said earlier, doesn't it? This here contradicts that m is the least upper bound, meaning that there is in some number smaller than m that can do this job. So it's a contradiction. Extreme value theorem. It's a terrible question, really bad, because it's just too, I mean, I'm not sure what they're expecting the student to do here in terms of proof, because they haven't covered their boundedness theorem. It's almost more of a topology question. I just think this is really poor. It's either making the student deliberately do some research in other books, or just having them really think about it but maybe not prove it. Maybe there's other ways to prove it. I'm not sure, but yeah, I don't like it, and I'm going to finish on a low note today.